Welcome to my talk, which is entitled Efficient Exploratory Clustering Analyses with Qualitative Approximations. My name is Manuel Fritz, and this is a joint work together with my colleagues Dennis Tschechow and Holger Schwarz from the University of Stuttgart. Our work focuses on clustering, and clustering has a particular exploratory power which fulfills several purposes, such as assessing the structure of the data in order to gain a better understanding of the data, grouping entities such that previously unseen entities can be assigned to a certain cluster, or compressing data in order to use this compression for further analysis steps. Note that wrong parameter values lead to imprecise results regarding the mentioned purposes. So that is, wrong assessments, wrong groupings, and wrong compressions can be performed. Now, what analysts typically do to achieve promising clustering results is to execute a clustering algorithm with varying parameter values, which can be very time-consuming. In our work, we consider this problem when using Casecenter clustering algorithms, such as k-means, for example. These algorithms are commonly used due to their simplicity, since an analyst just has to provide the expected number of clusters k. These algorithms proceed in a clear sequence of 3 steps. First, k-centroids are initialized. Second, in the improved clustering step, entities are assigned to the closest centroid. And third, in the check for convergence step, it is checked whether something has changed. So that is, if an entity changed its assignment to another cluster. And if so, another iteration is performed. And we call these iterations clustering iterations. Now the question is, how can we basically accelerate each single execution of a Casecenter clustering algorithm such that the whole exploration process can be performed more efficient? There is a plethora of related work in this area, and for a concise overview, I would highly refer to our paper. And for this talk, we aim to reduce the number of clustering iterations, since it results in shorter runtimes of a Casecenter clustering algorithm. And this can be particularly achieved when focusing on the check for convergence step, as highlighted here. Note that it is possible to explicitly limit the number of clustering iterations that should be performed. However, it is unclear how to define such a threshold, since too few clustering iterations lead to imprecise clustering results, whereas too many clustering iterations lead to long runtimes. And there is a prior work of us which also aims to reduce the runtime of Casecenter clustering algorithms. And this prior work is called termination via metalearning, or short MTL. The underlying idea is to trade off runtime with less quality, which is however still sufficient to achieve promising clustering results within exploratory clustering analyses. Here we provide an overview of the previously published metalearning approach. This approach consists of an offline step shown at the top and an online step shown at the bottom. In the offline step, several datasets with varying characteristics are clustered with different parameter values. And for each clustering iteration, meta-knowledge in form of clustering validity metrics are stored. And finally, a correlation between those validity metrics and the quality per clustering iteration is formalized. So for example, with a regression function. In the subsequent online step, a previously unseen data set is clustered. However, the correlation from the offline step is exploited in the check for convergence step, which enables to define qualitative demand regarding the clustering result. And therefore, the clustering algorithm stops early, so that is, it stops as soon as the qualitative demand is met. So while this approach may seem reasonable at the first glance, it is very obvious that the offline step is very time-consuming, since the clustering algorithm is executed on multiple data sets. And in this work, we want to tackle this problem. In this work, we present our novel approach, Generic Qualitative Approximation, or short GQA. In contrast to MTL, our novel approach explicitly avoids a prior time-consuming metalearning step and is therefore especially suited for ad hoc exploratory clustering analyses. Now, this approach relies on two properties. The first property, shown here on the left, states that the variance of the clusters becomes smaller per clustering iteration. And this property can be easily proved since the decreasing variance is basically the objective function of each Casecenter clustering algorithm. We denote the changes of the variances between clustering iterations as sigma, as shown here. And note that sigma typically becomes smaller per clustering iteration until it finally equals to 1. So that means the variance of the clustering result cannot be reduced any further. The second property is very similar to what you already saw for the meta-learning approach. We want to enable analysts to easily define an arbitrary qualitative demand where higher values correlate to better clustering results and lower values correlate to faster clustering results. Putting both properties together and using some easy calculus, we can define a new convergence criterion which can be used in the check for convergence step. And in easy words, this inequality shown here states that the clustering result changes less than the predefined qualitative demand. It should be emphasized that our approach preserves generality, since both properties are generally valid regarding dataset characteristics or Casecenter clustering algorithms. We have also formalized GQA and conducted a complexity analysis. And it turns out that our approach can be seamlessly integrated into the procedure of Casecenter clustering algorithms. Furthermore, it relies only on a negligible runtime overhead. And for more details, I kindly refer to our paper. In our comprehensive evaluation, we compare MTL and GQA in contrast to Spark's implementation of k-means. And for Spark's implementation of k-means, we explicitly did not limit the number of clustering iterations in order to investigate these differences in detail. We evaluated the performance on several synthetic and real-world datasets from different domains. And it turns out that GQA achieves tremendous speedups of up to 444x over Spark's implementation of k-means. And this correlates to absolute runtime savings of about 55 minutes. Since a promising clustering result consists of compact and well-separated clusters, we also investigated these two aspects in detail. So here, the differences of the clustering results in comparison to the clustering results of Spark's implementation of k-means can be seen. So the differences of the compactness are shown on the left-hand side, and the differences regarding the separation are shown on the right-hand side. In short, we summarize our results as follows. In general, we achieve very similar clustering results to Spark's implementation of k-means. So that is, on synthetic datasets, the clustering results differ less than 0.01%. And on real-world datasets, the clustering results differ less than 4% in terms of compactness and separation. So therefore, we can clearly state that GQA is able to achieve high qualitative clustering results. Summarizing both approaches, MTL and GQA, we can state that MTL achieves speedups of up to 669x. However, it requires a time-consuming offline step. And in our experiments, this offline step required several days. On the other hand, GQA achieves speedups of up to 444x, however, without the prior offline step. And therefore, it is a very strong fit for ad hoc exploratory clustering analyses. For both approaches, the qualitative demands are met in our experiments in most cases, which makes both approaches feasible for real-world scenarios. And finally, GQA typically achieves better clustering results than MTL in terms of compactness and separation. Concluding this talk, we presented a novel approach to terminate Casecenter clustering algorithms early based on an arbitrary definable qualitative demand. And this enables analysts to trade off runtime with quality of the clustering results. In our comprehensive evaluation, we unveiled that speedups of up to 444x for a single execution of a Casecenter clustering algorithm are possible, while the qualitative demand is met in most cases. Thank you very much for attending my talk.